And now we get to our last major proof technique, that is a proof by induction. And this is covered in the Book of Proof, section 10.1, as well as in Rosen 5.1. Induction is especially useful whenever you have a propositional function and you want to show that it is true for some infinite number of variables. So for example, if we wanted to show that some propositional function p of n is true where we have infinitely many n's that we can count. And countable here just means that we can, say 1, 2, 3, 4, etc. We can count them. So we want to show that it's true for infinitely many n's. So for an example of such a propositional function, you could consider something like the following. So this example asks us to show that 2 to the 0 plus 2 to the first all the way up to 2 to the n is the same as 2 to the n plus 1 minus 1. So you notice this part right here, that is our propositional function. That's our p of n. And this example is asking us to show that this is true for all n right here. So this is our infinitely many n that we have. So a proof by induction is especially useful whenever you're trying to show a statement like this. Propositional function is true for infinitely many n. So how exactly does a proof by induction proceed? So let's go ahead and look at the definition. So this definition is for statements that look like we want to show this propositional function is true for all n in the natural numbers. And how does this proceed? Well, there are 3 basic steps for a proof by induction. And the very first one is showing that p of 1 is true. And that's called the base case because it's the very first natural number that we're talking about. So it's the base case, show that p of 1 is true. The next step is called the induction step. And in this induction step, it asks us to show that p of k implies p of k plus 1 for an arbitrary k. And so we have an implication statement here that we need to prove, and we already have a bunch of different proof techniques that we know how to prove an implication like this. We could use a direct proof, proof by counterpositive, whatever you want, but in this induction step, we have to show that p of k implies p of k plus 1. And then after that induction step, we can simply conclude, and we are finished. We know that for every n in the natural numbers, this propositional function here is true. So that's the basic idea or definition of a proof by induction. And so again, we want to know, why does this work? How does it work that showing that P of 1 is true and then proving that this implication is true for an arbitrary k allows us to conclude that this propositional function is true for every n in the natural numbers? So I want to know, how does this work? And that's what we're going to explore in the next video.